Ship 37 achieved SpaceX's best landing yet, but turned completely orange during re-entry, revealing something unprecedented. This striking discoloration isn't damage. It's proof of Musk's secret active cooling test that could revolutionize reusability. Those distinctive patterns expose exactly how liquid oxygen experiments are pushing thermal protection beyond anything attempted before. What most missed? This failure might actually be SpaceX's biggest breakthrough. Let's dive right in. When Ship 37 touched down flawlessly after its latest flight, SpaceX achieved something remarkable. But the real story was written across its heat shield in striking orange patterns never seen before. After 3 consecutive flights ended in failure, with issues ranging from harmonic reactions to methane leaks in the nose cone. This landing represented a massive engineering victory. But here's what few people realize: that orange discoloration isn't damage at all. The orange coating appeared concentrated from the bottom of the payload section, creating distinctive patterns that had engineers talking. Most viewers assumed tiles had fallen off, exposing stainless steel structure to re-entry's 3,000-degree inferno. But the tiles appeared intact before the flip maneuver, and it's highly unlikely such a large area could lose protection simultaneously without visible impact. The real breakthrough lies in those distinctive inverted white V-shaped streaks at the top of the orange zone. When comparing pre-flight images, clear differences appear at these exact points. Locations where SpaceX installed metallic thermal protection tiles made from stainless steel. This represents a fundamental shift from traditional ceramic tiles toward a revolutionary metallic system that could change everything. But here's where the engineering gets fascinating, and most people overlook this crucial detail. The metallic tiles alone couldn't create such widespread effects. The scale suggests something much larger was at play. SpaceX's most ambitious experiment yet, with active cooling using Starship's own propellants. The evidence points to liquid oxygen as the secret ingredient. First, Starship carries significantly more liquid oxygen than methane. Second, only oxygen could produce the oxidation effects matching what we observed. The white V streaks likely represent liquid oxygen escape points, while the orange coloration shows how this coolant spread and reacted during re-entry's supersonic shockwave conditions. And here's what's truly remarkable. The oxygen either directly oxidized metallic tiles containing iron, creating iron oxide that spread across the vehicle, or leaked liquid oxygen intensified combustion during re-entry, altering tile appearance and creating that distinctive orange hue. Unlike theories suggesting heat shield failure, this indicates SpaceX successfully tested aspects of an active cooling system, technology that will be essential for Mars missions. But this is just the beginning. What's really surprising is how this single test flight could revolutionize the entire space industry. This heat shield development positions SpaceX at a critical turning point that most competitors haven't even recognized yet. While Blue Origin's New Glenn and ULA's Vulcan focus on expendable or partially reusable designs, SpaceX is pushing towards something no one has achieved: full vehicle reusability at orbital scale. But there's a detail that changes everything. True reusability isn't just about landing safely. Currently, even successful Falcon 9 boosters require weeks of inspection and component replacement between flights. Starship's heat shield faces an exponentially greater challenge. Thousands of ceramic tiles must endure temperatures that would melt steel, then be flight-ready again within days or hours. The traditional approach of replacing damaged tiles after each flight makes rapid reuse economically impossible. And that's exactly what SpaceX is trying to solve. This is where the metallic tile experiment becomes strategically game-changing. Metallic systems could potentially withstand multiple re-entries with minimal maintenance, slashing turnaround costs by orders of magnitude. The active cooling approach we witnessed suggests SpaceX is testing whether propellant-based thermal management can extend tile lifespan indefinitely. Why would SpaceX accept this enormous risk? Because the timing is absolutely critical. NASA's Artemis program requires heavy lift capability that only Starship can provide at scale. SpaceX's Starlink constellation demands unprecedented launch frequency. Future Mars missions need heat shields surviving both Earth and Martian atmospheric entries repeatedly. And here's what few people realize about the competitive landscape. If SpaceX cracks this code, they don't just win the current space race, they fundamentally alter the economics of space access forever. Launch costs could drop from thousands of dollars per kilogram to hundreds, opening markets that don't even exist today. But the real story gets more interesting when we look at what comes next, because this test was just proving the concept. The implications of Flight 10's orange heat shield extend far beyond a single test. SpaceX has one final opportunity in the V2 series with Flight 11, where Ship 38 will attempt the first return-to-launch site landing. Early images already show game-changing improvements, including distinct adhesive layers between tiles designed to prevent detachment during flight. If successful, this mission could see Starship caught by Mechazilla arms, proving full reusability is actually achievable. But here's where things get truly revolutionary. The transition to Starship 5 or 3, beginning with Flight 12 later this year, will incorporate every lesson learned from these thermal protection experiments. Most importantly, V3 vehicles are expected to feature fully metallic tile systems designed specifically for Mars-capable operations, where atmospheric entry heating exceeds anything Earth reentry can produce. What happens if SpaceX succeeds? We're looking at vehicles that can launch, land, refuel, and launch again within hours rather than weeks. This isn't just an incremental improvement. It's a fundamental transformation of how humanity accesses space. The wealth of sensor data from Flight 10 provides engineers with unprecedented insight into thermal protection performance under real-world conditions. And here's what's most remarkable about SpaceX's approach. Even failures accelerate development towards sustainable solutions. The orange heat shield patterns provide more valuable data than a dozen perfect flights because they reveal exactly how extreme heating affects different materials and cooling systems under actual reentry conditions. The broader space industry is watching with a mixture of admiration and concern. Success here could force competitors to abandon traditional expendable designs entirely, while creating economic pressure that reshapes the entire sector. But given SpaceX's track record of turning apparent setbacks into breakthrough innovations, that orange discoloration on Ship 37's hull may be remembered as the moment spacecraft reusability became truly practical. As we approach the 2030s and humanity's return to deep space exploration, rapid vehicle reuse isn't just an economic advantage, it's an existential requirement for making life multiplanetary. The lessons written in orange across Ship 37's heat shield might just be the key to unlocking that future. So what does SpaceX's orange heat shield really reveal? This is exactly why Musk has been so confident about Mars missions. They've been secretly proving that active cooling systems can work at reentry scales. Those distinctive patterns weren't failure marks. They were success indicators showing liquid oxygen thermal management actually functions under the most extreme conditions imaginable. What this means is we're witnessing the birth of truly reusable spacecraft, not the kind that need weeks of refurbishment, but vehicles ready to fly again within hours. This breakthrough positions SpaceX years ahead in the space race, potentially making Mars colonization economically viable for the first time in human history. And this is just the beginning. Flight 11's return-to-launch site attempt could prove the entire concept within months, while Starship V3 will implement these lessons on an even larger scale. We're looking at a future where space access costs collapse and humanity becomes a truly spacefaring civilization. But here's what I want to know. How do you think this thermal protection breakthrough will impact the timeline for Mars missions? Will other companies be forced to abandon traditional heat shield designs entirely? This is Future Space, and we dive deep into the breakthroughs that are reshaping our cosmic future. If you want more analysis that goes beyond the headlines to reveal what's really happening, hit that subscribe button. Because the next decade in space exploration is going to be absolutely revolutionary, and you won't want to miss a single development. When SpaceX chose stainless steel over aluminum for Starship, industry experts questioned the decision. But Elon Musk just revealed why this risky choice is actually genius engineering. While aluminum melts under re-entry heat, Steel withstands both rocket engine flames and atmospheric heating without complex paint systems. But here's what most people miss. This isn't just about durability. This material breakthrough enables something revolutionary, rapid reusability that could turn space travel into routine transportation. Let's dive right in. Here's what makes SpaceX's material choice so revolutionary. When the entire aerospace industry has relied on aluminum for over 60 years, Elon Musk's team made a decision that seemed almost reckless, switching to stainless steel. But the engineering reasoning behind this choice reveals a level of strategic thinking that's reshaping space exploration forever. The thermal challenge with aluminum becomes crystal clear when you dive into the numbers. Aluminum's melting point sits at 1,220 degrees Fahrenheit. Sounds high until you realize Starship's Raptor engines blast flames exceeding 6,000 degrees Fahrenheit during operation. During atmospheric reentry, the spacecraft faces temperatures spiking to over 2,500 degrees Fahrenheit. Aluminum simply disintegrates under this dual thermal assault without massive, complex protective systems. But here's where most people miss the genius. It's not just about raw temperature resistance. Steel maintains its structural integrity across these extreme thermal ranges. But the real breakthrough lies in thermal cycling behavior. Every time you load cryogenic fuel at negative 297 degrees Fahrenheit, then fire engines at 6,000 degrees Fahrenheit, you create massive thermal expansion and contraction cycles. Think of it like repeatedly dunking a metal ruler from ice water into boiling oil. Aluminum develops microscopic stress fractures that compound over time, eventually leading to catastrophic failure. Steel's crystalline structure handles these thermal shocks with remarkable resilience, actually getting stronger through controlled stress cycles. And here's the game changer that traditional aerospace completely overlooked: paint and coating systems. Conventional rockets require intricate multi-layer coating systems to protect against corrosion, heat, and aerodynamic stress. These paints crack, peel, and degrade during extreme temperature cycling. The space shuttle, for instance, required teams of technicians spending weeks carefully inspecting and replacing thousands of thermal protection tiles after every flight. Steel's natural oxidation resistance eliminates this entire maintenance category. No complex coatings, no paint systems, no tile-by-tile inspection protocols. The rocket literally takes care of itself through controlled surface oxidation that actually enhances thermal protection over time. The operational numbers reveal the magnitude of this breakthrough. NASA's Space Shuttle program required an average of 9 months of heat shield refurbishment between flights. SpaceX targets less than 1 hour turnaround with their steel heat shield system. We're talking about a 99.99% reduction in ground processing time, transforming space access from a months-long industrial process into something approaching airline operations. SpaceX has already demonstrated successful atmospheric re-entry and precision landing multiple times with their steel design. But they've also encountered the expected learning curve, shedding heat shield tiles during several test flights. Musk openly acknowledges they need to fine-tune tile thickness, adjust gap spacing between tiles, modify underlying attachment systems, and optimize the substrate materials through repeated flight testing. What's fascinating is their approach to this iteration process. Instead of spending years in ground testing like traditional aerospace, they're using actual flight data to rapidly evolve the design. Each flight provides thermal data impossible to replicate in ground facilities, accelerating development cycles from decades to months. But this is just the beginning. What's really surprising is how this material choice unlocks operational capabilities that seemed impossible just 5 years ago. This steel breakthrough doesn't just improve SpaceX's rockets. It fundamentally repositions them in a market category they've essentially created alone. While established aerospace giants like Boeing, Lockheed Martin, Blue Origin, and international competitors focus on incremental improvements to proven aluminum designs, SpaceX has leapfrogged into an entirely new operational paradigm. The competitive implications are staggering when you analyze current industry turnaround times. Traditional launch providers operate on 6-month to 2-year cycles between flights. ULA's Atlas V and Delta IV rockets are completely expendable, destroyed after single use at costs exceeding $400 million per launch. Blue Origin's New Shepard, despite being reusable, requires weeks of inspection and refurbishment between flights. Even SpaceX's own Falcon 9, revolutionary for pioneering commercial rocket reusability, needs several weeks of processing between missions. But Starship's steel architecture targets